And now, let me move to lecture note. Then let's try to read the statement that we are going to solve. Okay, so please give a pause of this video and please try to read this statement very carefully and write down what you know and what variables are given, and from those given conditions how we can tackle this problem. Okay, so now again, and we want to do the ideal diesel cycle analysis, and that diesel cycle has a compression ratio of 18, and now we also know the initial temperature and the pressure, which is 300 Kelvin at 0.1 megapascal respectively. And now we also are given cutoff ratio. As I said, that is another very important design parameter of the diesel cycle, which is now 2. And let's try to assume that we use the ideal gas of the air, okay, that has a constant specific heat, and we also are given Cp value and Cv value. Now let's try to calculate the temperature and pressure at the end of each process of the cycle. So now we know the state 1, then we also have to calculate 2, 3, and 4. And once we know the pressure and temperature at all states, then actually we can move on to the next questions to calculate the specific work per cycle. Now that is the work per cycle per unit mass of the working fluid. So the unit should be kilojoule per kilogram. And then the next one we have to calculate is the mean effective pressure, which is given in terms of megapascal. And the last question is the thermal efficiency calculation. Okay, and I found that we have one error here, so it should be 3 and 4. Okay, so that is just trivial, but I just want to make it clear. So now here we have a summary of the given conditions. Okay, so we know the compression ratio, which is 18. Okay, and this compression ratio is written as V1 over V2. And now we also know the cutoff ratio, RC, which is V3 over V2, and that is given as 2. And also we know the initial temperature and initial pressure. Now the assumption is that the air is the working fluid, and that is ideal gas and with a constant specific heat. And now I really truly wish that now you should be able to calculate the K value, the specific ratio, and gas constant from the given Cp value and Cv value. Okay, so now R is Cp over minus Cv, and K is Cp over Cv, so you can calculate K and R. And also let's ignore the kinetic energy and potential energy of the piston. Let's try to calculate each state of temperature and pressure. So now I'm not going to solve all these process for this diesel cycle analysis, because now we already learned how to do that in the spark ignition engine. So I'm going to use most of the process we already learned how to do that in this slide. So let's try to calculate the reversible adiabatic compression process, which is isentropic. Right? Now, because we already assumed the ideal gas with a constant specific heat, then we should be able to use this equation, which is the equation for isentropic process of ideal gas with constant Cp and Cv. Right? Again, this equation is should be only used for this condition. Okay? But anyways, we use this equation. Now we know V1 over V2. Okay. Oh, by the way, let's go back. So from the given T1 and P1, we can calculate the specific volume V1, which is RT1 divided by P1, and now we know that is 0.861 meter cubic per kilogram. Then, by having the compression ratio, V1 over V2 is same as the compression ratio. So now we have this equation which gives us the pressure at the end of compression process, okay, which is 4.95 megapascal. And also we can calculate the specific volume at 2, which is from the compression ratio. So now we have this value. And by knowing the pressure and the volume, then we can calculate the temperature at 2, which is 824.4 Kelvin. Now, let's move on to the second process, which is constant pressure heat input process. So because we are talking about compression pressure, we now know that pressure should be constant. So that is what we have. And how about V3? The specific volume at 3 can be calculated from the cutoff ratio. Okay? And because we already know V2, so we can calculate V3, which is given as this equation. We can calculate that. And again, by knowing P3 and V3, we can calculate T3 using the ideal gas law. And now we have this value, which is pretty high temperature at the end of heat input process or combustion process. Then also we can do exactly the same thing for the reversible adiabatic expansion or isentropic expansion. Again, we use the same equation as we used for the compression process. Now we calculated P3 and we also know V3, and V4 is same as V1. So we also know everything. So it can calculate to be 54.9 kilopascal. And in terms of specific volume, now we are talking about this process where the specific volume at 4 should be the same as specific volume at 1. I already talked about it, right? So that is here. And by knowing P and V, so we also can calculate the temperature at the end of expansion process, which is around 764.7 Kelvin. Still, even after expansion process, and that is ready to be exhausted, basically whole rejection process should happen, but that temperature is still pretty high. And that is basically waste of this energy. And we are going to, that is pretty big loss, and we somehow have to think about a way of how we can effectively use that high energy burn gas. There are many technologies to make use of it, but at this moment we have to stop. Anyways, but you should be, you should remember that the 4 at the process at 4 still it does have certain energy that we should not use, and we just expel it from the engine. Okay, now let's move back to the lecture note. So based on all values of pressure and temperature at each end of process, and now how can you calculate the specific work per cycle? Okay. Now, as I already explained earlier, we can write up the net work per cycle. In that case, just let me write it in terms of per unit mass or specific. That can be written as in Q in minus Q out, right? Or we can calculate in terms WE minus WC. No matter what relation you use, we basically should have the exactly same value in terms of W net. But in order to calculate the expansion work, we have to think about two terms. One is expansion work during the constant pressure heat input process, and another part of work during the expansion process. Many times, many students make a great mistake, big mistake, by not considering this part. Okay, so sometimes they just wrong because simply they ignore this. So you always have to be careful when you try to use this equation to calculate the net work. Okay. Now the unit of this should be kilojoule per kilogram. Okay. Now let me just try to use this equation because that is easier for me. So with that being said, how we can calculate Q in? Okay, so that happens during the process 2 to 3 heat input process. Now we can write the first law during this 2 to 3 process, which is U3 minus U2 equals to Q in minus, right, W 2 3. Okay. But now this W2 3 can be calculated in terms of PdV. Now we are talking about constant pressure process, so we have to have P2 V3 or V2, right? Then by moving this term, actually you already did that kind of solution, very similar solution in exam 2. But anyways, so from this equation, Q in can be written as H3 minus H2, right? So that is Cp T3 minus T2. Now we can calculate that as this value. Okay. Now, how about Q out? So that is process from 4 to 1, and with the same way we have to use the first law of thermodynamics, and what we have is U1 minus U4. Remember, in that case 4 is initial state and 1 is the final state. So that is minus Q out because we know that is heat loss, and minus W4 to 1, but that should be 0 because that is constant volume. Now, so Q out can be written as U4 minus U1, which is CV T4 minus T1. That gives us 381.05 kilojoule per kilogram. So now we can calculate the specific net work per cycle as Q in minus Q out, which is 531.2 kilojoule per kilogram. Okay. Right, then the next question is the mean effective pressure, or MEP. So please remember that the MEP is defined as the net amount of work divided by the displacement volume, or maximum volume minus minimum volume. So in that case, it should be V1 minus V2. We already calculated W net, and now we also know V1 and V2. Okay, so we can calculate this MEP, and the number is 0.65 megapascal or 650 kilopascal. Okay, so that is another way to express how can I say, so work output perspective. Okay, but instead of using kilojoule or kilojoule per kilogram, we use kilopascal. Okay, now how about the thermal efficiency? Again, the thermal efficiency is defined as W net divided by heat input, or in the case, let me just try to change that to Q in because we already use Q in. So we already know W net, we already know Q in, so we can calculate thermal efficiency, which is 58.2%. So that is it. So you have to always think about why we should all these kind of calculations which look really complicated. because we always want to know the net work of the cycle, or in that case, a diesel cycle, and thermal efficiency. And in order to be able to calculate these two, we have to know all properties at each state during your cycle. Okay? So that is general procedures of doing thermodynamic cycle analysis. So that's it. But let's just discuss a little bit more about the thermal efficiency. So particularly for the thermal efficiency of the ideal diesel cycle.